Chris for the very kind introduction. I want to talk today about work that we've been doing for the past few years now in terms of trying to elucidate and potentially control coupled oxidation and reduction cycles over metal catalysts. When we look at, say, reduction, we recognize that something is being oxidized along the way, hydrogen typically, and when we look at basically oxidation, something is being reduced along the way, say oxygen in those particular systems. So we have coupled oxidation and reduction cycles. Nature does this very, very well, very nicely and exquisitely. How does it do that? Well, effectively you've got this molecule here, nicotinamide adenine dinucleotide, which we'll abbreviate as NADA+. And NADA+ acts as a co-catalyst, basically to allow you to oxidize your alcohols, in this case, or carry out glycolysis of the alcohols. And in the process, it creates basically NADH. In terms of, I'm losing my pointer. In terms of NADA, it is a molecule shown here. This one lost the pointer as well. So NADA plus basically is very easily reduced in this system by the addition of protons as well as electrons. We'll pick up basically those very easily from the molecule as being oxidized. And vice versa, you can take this molecule once you've made it and transfer electrons back, allowing for the oxidation in that particular system. So NADA is basically reduced to form NADH. NADH then reduces oxygen to form water, and ADP to form ATP in the system, ultimately giving you energy. So a very close interacting cycle. This is acting as a co-catalyst inside the oxoreductase enzyme. The enzyme itself cannot carry out the chemistry. It only works in the presence basically of these co-enzymes or co-catalysts. I hope to show you that what we have in electrocatalysis as well as heterogeneous catalysis is systems that behave quite similarly. So we'll start by looking at electrochemistry, but I want to use this just as a platform to talk really about heterogeneous reactions. In terms of coupled cycles, the easiest place to look is really a fuel cell. At the anode of the fuel cell, you're carrying out oxidation of the alcohol, effectively taking methanol, oxidizing it with water, forming CO2. You generate protons, you generate electrons. Protons transfer through effectively the membrane, electrons through the wire, and they recombine ultimately at the cathode. The cathode is carrying out basically reduction of the oxygen to form water, picking up those electrons and protons. So you have to worry about how fast the oxidation occurs and how fast the reduction occurs. They communicate with one another. Two coupled cycles. As we look at this, I won't go into gory detail, but methanol, we did this as a function of potential, as a function of solution, is ultimately oxidized to form a hydroxymethyl. It goes on to form formaldehyde, and then on to CO. Platinum tends to be one of the best catalysts for this, for carrying out these transformations. The problem is platinum is also poisoned or blocked by CO that builds up on the surface. So we end up with this dead end. You do get CO2. You can enhance this significantly if you add an oxophilic metal, such as ruthenium or molybdenum, to provide OH sites that would ultimately catalyze the CO2 in the system. So if you look at this next step, if I'm going to carry out and try to add, this is a platinum are shown in brown, ruthenium are shown in orange. Ruthenium will selectively or tend to strongly bind water to the surface. If I did this in vacuum and I were to activate it, I would form an OH group and a hydrogen on the surface. Without a potential even, if the work function of the metal is high enough, it'll suck an electron out and you would generate protons that can go off in the solution. That's what you'll see here. These are ab initio molecular dynamics movies. So the water here is ultimately activated. We form a hydronium ion in the process. OH is now basic. It picks up an electron and will allow me to pull off a proton from this water molecule. And it's going to pull off a proton from that water molecule. So what we end up with is basic OH groups on the surface and transfer of, it looks like OH is migrated, but it's not. Simply proton-coupled electron transfer. This is a Grotius mechanism when you talk about biological systems. So I want you to remember this. We'll see this come up again in a bit. The subsequent oxidation then is once I form that OH, typically on the ruthenium sites, shown in yellow here, and CO is covering the platinum sites shown in green. OH undergoes a nucleophilic backside attack. You transfer an electron into the CO2, it's bent, and once the CO2 forms, it kicks an electron in, it comes off as a linear molecule and spits out a proton. Again, proton-coupled electron transfer in these systems. So remember that one as well. We'll see it again also. We move over then to the cathode. It takes the protons and the electrons that form and ultimately reduces oxygen in those systems. This is on a platinum electrode. Effectively, O2 comes in. If the surface is covered in hydroxyl groups and water, and you can't directly dissociate at the potentials you're operating at, instead you undergo a proton-coupled transfer where you add an electron to oxygen first, and then almost simultaneously, you get a proton transfer. You form the peroxo intermediate, and then this can easily dissociate on the surface. And so we can show that we've done this as a function of potential, as a function basically of different conditions, and you can see how the barrier changes as a function of the reaction potential. And it matches up fairly nicely with some of the literature data that's looking at the overall reaction to carry out reduction. Okay, that's the preamble to what I'd like to talk about. And I'm going to talk about 3 different example systems, and I hope to show you that they have these coupled cycles together, and that one can derive or see catalytic intermediates that drive these chemistries. My first example is work we did some years back now with Bob Davis. Bob elegantly showed that bulk gold can carry out the oxidation of polyols in the presence of oxygen, but you needed a little bit of base. You needed the oxygen, you needed base. This is in water, and it can be done at low temperature. I won't go through all of the details. We've done that in the past, but I simply want to point out in the absence of base, turnover rates are 0 or 10 to the minus 2, 10 to the minus 3, very, very low in these systems, on gold as well as platinum and palladium. You add a small amount of base into the system, and the turnover rates now are almost 4 order of magnitude higher, and on gold it's 1 order of magnitude higher than on platinum and palladium. Surprising, because gold usually doesn't carry out oxygen, oxidation, at least bulk gold. We make our jewelry out of it. So this was surprising and interesting, and we know from surface science that we don't typically activate OH bonds, we don't activate CH bonds on gold surfaces, and so how is that chemistry occurring? Effectively, it's the base that we add in the system. So you have OH minus either in solution or on the surface is undergoing a deprotonation. And I showed you that earlier in the fuel cell. You're simply doing a proton transfer from water. Here it's from the alcohol. You form an alkoxide, a second OH molecule on the surface will pluck off this hydrogen that's partially acidic and effectively give you the aldehyde in the system. So you've oxidized to the aldehyde. The next case is then to carry out the oxidation. Just as we saw previously in oxidizing CO, there's a nucleophilic backside attack. OH carries out the same chemistry here. And then we undergo one more subsequent step to deprotonate this to give us the acid. That is the product in this system. So I've walked through all of the steps, and we've never used hydrogen or oxygen in this system. OH was my oxidant, carried out all the oxidation chemistry. So why is it that this chemistry does not run unless you have some oxygen present in the system? Well, oxygen, we believe, is playing the same role as it does in the fuel cell. It's picking up electrons that are being formed in the process. We know that oxygen won't dissociate over bulk gold 111 surfaces, but we also know from fuel cell literature that in alkaline media, these are pretty good cathodes for carrying out chemistry. And that's due to the fact that effectively it will pick up electrons, it will pick up protons, and proton-coupled electron transfer in the same way it did it on platinum in the fuel cell system. Electron transfer activates the molecule followed by proton transfer. This weakens the oxygen-oxygen bond. At some point, we can then readily split and form OH groups. So I've regenerated the OH groups that I've started with. What I have is a local electrochemical cell. Effectively, I'm feeding in an alcohol. It's oxidized by the hydroxyl or the base that's added to create the acid. I generate 4 electrons. I can't continuously build up electrons in that system. They have to go somewhere. And so where they go is effectively into the O2 to activate the O2. Along with protons from water, they regenerate the 4 hydroxyl groups. It's dictated by the rate of how fast you do oxidation and the rate of reduction. Both of them are coupled together. And if you look carefully at this, OH is added. It's basically a co-catalyst in this system. It's regenerated. It's the same idea that you saw in the enzyme. NADH plus in that system activated the alcohols to do glycolysis in our body, and ultimately is regenerated in the process. Fast forward another year or a half forward. This is work that we were doing then, or this was work done by Maria Sed and Enrique Iglesias, where they were trying to use alcohols, alkanols, and alkanals coupled together with a little bit of hydrogen to carry out deoxygenation, alkanol gas shift, if you will. And you see those products, but was surprising, you saw many more products coming from condensation as well as esterification. You were forming carbon-carbon bonds, growing carbon chain lengths, and undergoing carbon-oxygen bond additions over copper and silica. These are typically acid-base catalyzed reactions, so that was surprising. I don't know where the acid sites are in copper. I don't know where acid-base sites are in silica. After examining this for a while, we recognized that when I undergo this equilibrium reaction, I'm forming basically an alkoxide. An alkoxide on a group 11 metal. It'd be similar to what I just showed you. OH minus on gold, this is RO minus on copper. Indeed, when you look at electronic structure calculation, there's a negative charge that builds up basically on the reactive moiety, and this can undergo base catalyzed reactions. It's a base that is formed in situ, basically, in the chemistry. So we start with an alkoxide. It can readily react, basically, with a neighboring propanol molecule, again, through a nucleophilic attack, the same way the OH activated effectively the other carbonyls in the previous examples. You form the transition state, you form a beta alkoxide. You can subsequently then remove this either through CH bond activation by the copper. That tends to be difficult on the surface. Instead, you do that through a co-adsorbed alkanal on the surface. Will readily undergo hydrogen transfer reactions. So this hydride gets picked up basically by the alkanal, and I regenerate basically my alkoxide. So this is my active co-catalyst. It's formed from the initial reagents, and effectively it's reformed through hydrogen transfer reactions. So it's again behaving as a co-catalyst to drive this chemistry. Let me put these two reactions sort of side by side. On the left is the work on gold, where OH was added specifically, and on copper, effectively, we were generating this through the addition of hydrogen, basically in an alkanal. And so this is made in situ, if you will. This was added. Both of them are acting as oxidants. They add to the alkanal. This one creates an acid. This one creates an ester. Subsequently, we activate the final CH bond. In this case, we reabsorb oxygen. It picks up the electrons and it picks up a proton undergoing a reduction reaction. So O2 is being reduced. The OOH is carrying out the oxidation to reform basically the catalyst. So oxidation reduction. In this case, it's not O2, but it's the alkanal double bond that picks up basically the hydrogen from the previous molecule and regenerates the catalytic sites. Both of them are showing the same thing that the enzyme does. These are the NADH plus intermediates allowing you to oxidize basically these molecules. Fast forward about another year and a half or two, more than that I think now, later, and we started to do some work with David Flaherty and Jason Adams looking at not oxidation, but on reduction. And I hope to show you that you see the same things here as well. So this is looking at the reduction of oxygen to form hydrogen peroxide. We want to do this because it's microbial that can be used basically to disinfect and purify water. And you'd like to do this in a direct manner, so on a heterogeneous catalytic surface if possible, and do this with a benign solvent if possible. It's been shown to work on palladium. Dave and Jason had a talk earlier in the week. The selectivities are somewhat low on pure palladium. You can increase selectivity in these systems to 60 and 70% if you do this with acidic solvents, adding halides, or if you begin to alloy the palladium with gold in these systems. I'm going to look predominantly at palladium and what happens in acidic solvents. We can start by looking at what happens on a metal surface with oxygen, palladium substrate. Oxygen, as you might expect, would absorb. It can undergo hydrogen addition, has somewhat lower barrier to form a peroxo species, and then it can subsequently dissociate fairly easily. What you note in all these cases, you get dissociation, not very difficult. You would expect that. Palladium is a good electrode for carrying out basically the cathodic O2 activation to make water, 4-electron process. We don't want this, right? We want the 2-electron process, and it tells us that anything that's basically giving you larger ensembles of palladium is going to lead to water, and you don't want that. So likely what's contributing to the activity and the selectivity in this process are surfaces that are more likely covered with oxygen. They see that from the X-axis, that the surface layer has oxygen, basically covering in part of the surface. You carry this chemistry out now in different protic media. You see fairly reasonable rates of reaction. You carry it out in aprotic solvents, and these are dead. So the protic solvents are important for driving this chemistry. We'll start by looking at what happens with water. So in the presence of water, these are Jason and Dave's results. As you increase the pressure of oxygen in the system, it is first order, the rate in oxygen. And then as you go to much higher pressures, it becomes zero order in oxygen. As you look at changes in the hydrogen pressure in the system, what you see that is first ordered hydrogen, and then at the range you'd probably be operating at becomes effectively zero order or half order in oxygen or hydrogen. In both cases, you see this discontinuity. This discontinuity was figured out basically by Dave and Jason working with Iman Karen and his student Yuming Liu at Virginia Tech, doing X-halves and doing great characterization work to show that what's happening here is the formation of a hydride. In water, you have to go to somewhat higher pressures, and then you begin to form palladium hydride that is carrying out the chemistry of the system. When you look at putting a model together to try to describe this chemistry, we put together a Langmuir-Hinchelwood model. We can't describe the zero order in oxygen or the zero order in hydrogen due to the fact that you have two terms here requiring two sites and a squared term here. I either get first order or I get negative first order. I can't describe that zero order behavior. So it suggests that something is not quite right with this. And when you carry out the calculations, you understand why. If I try to take hydrogen and directly add it from the surface, it's hydridic in character, and it's trying to add to a negatively charged oxygen. So the barrier is higher. In the presence of water, you can carry out proton-coupled electron transfer reactions, again dependent upon the metal if it will pick up an electron. So it depends on the work function. You see that indeed that's the case. It costs you about 30 kilojoule per mole. You generate protons, you generate electrons, and in the rate limiting step, there's an electron addition followed by basically a proton addition to this surface intermediate. This then does not require an extra site on the surface. So if you carry out the same model, it's a proton and an electron with a single site. This will explain the rate orders that we're seeing experimentally. So this system is looking a lot like the example that you saw for the oxidation of the alcohol on gold. In this case, you're oxidizing not the alcohol, but you're oxidizing hydrogen. You create two protons and two electrons. The protons come over and they add effectively to the O2. The two electrons add to the O2, and you generate basically hydrogen peroxide in the system. You try to look at other alcohols and methanol, you see the rate is significantly higher, but then decays very rapidly over time. We believe that's due to the fact that you're building up some sort of hydrocarbon intermediates. You see that in some of the products. You form formaldehyde. And so that's doing something, we believe, growing carbon-carbon chains perhaps on the surface. But the rate is higher, and if you add basically the alcohol to the water to the alcohol, you can stabilize the rate a bit, and these rates are even higher ultimately in water and methanol and water systems. So what happens basically in the alcohol, methanol in this case? It's zero order again in oxygen over a wide range of pressures, and you find that in this particular case what's happening is that these are palladium hydrides over this wide range of pressure. So the alcohol is basically stabilizing the hydride phase of palladium that is doing the reaction chemistry. Again, you see first order in O2, maybe half order up here, and then zero order in hydrogen in the system. So the same sort of reaction kinetics that you saw earlier, except we don't have the discontinuity, we have a hydride phase over the entire range. So we thought, well, looks like maybe it's the same chemistry. So you carry out the same chemistry of doing a proton-coupled electron transfer to the O2 from the methanol now, and effectively the barriers are the same, the overall reaction energies are the same, and in retrospect, looking at it, they should be the same, right? I don't think this alkyl group is playing much of a role in changing all of that. We saw that the kinetics, however, are quite different in the alcohol versus the water. So something is going on, and what you see in terms of the products, you're forming hydrogen peroxide, but you're also forming formaldehyde along the way. So where do we see formaldehyde formation? Yes, I think back to Iglesias' work, they had a couple of an alkanol and an alcohol in that system. And so perhaps we have the same thing, as the alcohol is going back and forth to create these intermediates. So we say, let's look at the equilibrium between formaldehyde and methanol in this system. And I'm going to start really from the formaldehyde side. You can add hydrogen to it and form the alkoxide the same way we did this on copper. And then they can go on to form methanol. The problem with that is I'm taking a hydride from the alkoxide and now trying it to add to the O2 in the system. It may be a little bit challenging. The alternative is instead I add hydrogen to the oxygen end of the molecule. I make a hydroxymethyl. It's a bound species through the carbon. And then I undergo a subsequent step to make the methanol. Here I would be transferring from this intermediate a proton and an electron to the oxygen. Maybe a bit more favorable. Indeed, that's what we see. When you carry out the calculations, hydrogen dissociates, hydrogen adds to formaldehyde. It's the methoxy path. You undergo a subsequent hydrogenation step, and then you remove methanol. If instead, from this point, you add the hydrogen to the oxygen, you find that this energy is significantly lower, this path is significantly lower. On palladium, it forms a very strong metal-carbon bond, and so it prefers to go through basically the hydroxymethyl intermediate. So this hydroxymethyl intermediate basically is formed on the surface, and perhaps is playing a role as a co-catalyst to drive the chemistry. So we carry out the calculations for that, and indeed that's what we find. Again, the model that we have is we have a palladium hydride. Oxygens have to be covering the surface, otherwise we would get complete reduction to water. And effectively, these guys are bound to the surface. They readily transfer a proton and electron to activate the O2 bond. This barrier here is only 10 kilojoule per mole. The second molecule then is used basically to shuttle a next proton and electron in the system. I form hydrogen peroxide. This barrier also is only 8 kilojoule per mole. Put them together, the overall apparent barrier here is about 18 kilojoule per mole. And under the reaction conditions, it changes somewhere between 10 and 20. At the higher pressures that we're operating at here, it's about 17. So reasonable comparison with the experimental results. So what we have, again, is the same sort of cycles we've been talking about before. Is I have effectively an alcohol that's generating this hydroxymethyl, and this is being used as a co-reagent or co-catalyst to reduce oxygen to form hydrogen peroxide. It then must be regenerated. It's regenerated by having hydrogen present. What about the selectivity in the system? Well, with this species on the surface, it can undergo a proton-coupled reaction to directly form water, where you split the bond. This barrier is 44. If I try to directly activate that bond, even higher energy. And so these are much higher energies in the selected path to form hydrogen peroxide in that system. And so effectively having the hydride and having high surface coverages of oxygen slows down or inhibits this particular pathway. This is seen experimentally. As you increase the hydrogen pressure, the activation enthalpies measured effectively go up to form water in that system. That's exactly what we're finding. When we increase hydrogen on our surfaces, subsurface, it makes this more difficult. What's happening when you look at the palladium metal versus the hydride, there are vacant states near the Fermi level. They allow you to interact with the oxygen, dissociate the oxygen, and on the hydride, effectively, those states are nearly filled, making it more difficult to activate the O2, leading to the higher selectivity. In the opposite cases, you increase the hydrogen, you increase electron transfer, which is driving some of this chemistry, and so these barriers go down. And we see that as well in the calculations. The higher hydrogen that we have in these systems lead to lower activation barriers. Let's look at kinetic isotope effects. If you deuterate the alcohol, methanol in this case, what you find is there is a kinetic isotope effect, which suggests that the OH bond is involved in the active transition state. That's what we see here, is these OH bonds are playing a role to activate and lead to the final product, consistent with the KIE values here. You also look at the case of hydrogen versus deuterium, and it shows a kinetic isotope effect. That could be directly from hydrogen adding to the oxygen on the surface, but I showed you earlier those barriers are significantly higher. And we would not explain really these kinetic isotope effects for the OH groups. Instead, what they refer to is the fact that you have a pre-equilibrium step that hydrogen is basically adding to the aldehyde to create our hydroxymethyl, our co-catalyst, to drive this chemistry. So come back, and what we have again is this cycle. We start with methanol, it's activated, forms the hydroxymethyl. You adsorb O2, it's using its electron and proton basically to transfer. You form a peroxo intermediate, it becomes formaldehyde, it's rehydrogenated on the surface, basically to give you this intermediate back, which carries out a second step. So this species is a co-catalyst that's continuously regenerated in the process. If you add, and you can see this, if you do this in water and you add formaldehyde, the experiments Jason did show that you can show significantly enhanced rates by no alcohol here, but simply adding the formaldehyde. So I want to show you that this connects with other things in the literature as well. And so people are looking at these coupled cycles and adding in other intermediates, co-reagents, or co-catalysts. Tempo, for example, aids the oxidation of alcohols. This is nice work by Shannon Stahl. Using this tempo molecule, it aids in the activation of this OH and CH bonds. You get an aldehyde, and you form tempo H in this process. The tempo H then is used to reduce oxygen. In that case, they go all the way to water. It's the same cycle you saw here, except we're starting with formaldehyde going bound to the surface, going to this hydroxymethyl. In fact, I would argue these are very similar in terms of how they act. This guy is easily to transfer protons and electrons because the nitrogen and the tertiary carbons on that molecule stabilize hydrogen transfer. In our case, in the gas phase, this wouldn't be very good, but on the surface, I've got a metal to donate electrons, and that aids in the easy activation of that OH bond. The metal here is acting as a ligand to drive this chemistry. So you can use basically pulling off a hydrogen. The dehydrogenation energy of tempo is 285. You do this for the hydroxymethyl, it's only 10 kilojoule per mole higher. Go back to the biological system. NADH basically is 310. These are all similar to one another. We believe they're all acting as co-catalysts to couple these oxidation and reduction cycles. So to finalize this methanol case, effectively you're taking an alcohol, it activates to form this co-catalyst, it drives 2 protons, 2 electrons, to activate O2 to give you dioxygen, and then it's ultimately regenerated by hydrogenation of the formaldehyde that forms. Let me summarize. I tried to show you 3 different example systems from heterogeneous catalysis that relate to electrocatalysis and biological catalysis. The first was the work by Bob Davis's group, where they're using gold. Effectively, you added the co-catalyst OH. It carried out the oxidation of the alcohol, basically to give you an acid, and then it generated basically electrons in the system, and you needed to put in oxygen. Oxygen was reduced to regenerate that co-catalyst. So oxygen then was reduced to give you the OH. In the second example, we did the same sort of thing, except rather than adding OH, it was generated in situ by a hydrogenation to form an alkoxide. It adds to basically the carbonyl group, giving you an ester rather than an acid, but it's the same idea. Ultimately then you take an aldehyde rather than oxygen, you pull off the electron and the proton, and you regenerate the active site to carry out this chemistry on the surface. Finally, we started with an alcohol. In this case, we were more interested not in the oxidation, but we were interested in the reduction reaction. The oxidation was used to generate effectively the co-catalyst. It then allowed for the reduction of oxygen to form hydrogen peroxide, and then hydrogen was used to regenerate basically that active site. All of these, I would say, look to me similar to how enzymes carry out oxidation and reduction. The NADH+ is carrying out basically this facile proton-electron transfer reactions to carry out both reduction and oxidation. I'll stop here and thank the people who did the work, Ashwin in my group, Jason, and Dave's group, Stuart, Wenji, Dave Hibbett's, a range of other folks, people we've interacted with, Bob, Enrique, Dave, and Iman, and Glenn Tumley from BP, financial support, computational support, and you for your attention.
All right, we have time for some questions.
Hi, I'm surprised in your atomistic pictures, at least, in what mechanism you didn't neglect it, but there's a mechanism that Karen Goldberg proved happens for palladium complexes, hydrido complexes. The palladium hydrogen bond interacts with O2 quite easily to where the O2 just inserts directly into the palladium hydrogen bond to make the OOH species. And you didn't seem to look at the possibility in your calculations for that energy diagram.
We looked at, we did look at the direct addition to the O2 that was bound. It was 40-some kilojoules, about 20 kilojoules.
The addition of a hydrogen to the O2 that was bound. Why not just the O2 coming in from the gas phase inserting in the palladium hydrogen bond? Which you could do in a situation where you were limited with single palladium center surrounded by other things that were blocking it, and it would be more selective chemistry then.
Yeah. I mean, this is done, and also what's different in versus in the gas phase, this is done in the presence of solution. But we can look at
O2 coming through the solution. I mean, she's got solution also in her experiment. But then another bone to pick. Could you go back to the 2 slides before the summary? As a surface scientist, knowing when you have an adsorbate like the bottom one in the right-hand diagram, how little the vibrational spectroscopy of that OH bond is influenced by the platinum being bonded to the carbon down there, as opposed to just hydrogen being bonded to the carbon down there, or another carbon being bonded to carbon. I'm surprised that is such an active hydrogen, as the hydrogen is on the complex on the left, which was designed to have a very active hydrogen.
I think the issue is wet as a stable species on the surface, behaving like a hydrogen that's keeping the electron here in the metal. When I undergo a deprotonation reaction,
what's the OH stretching frequency for the species on the left? What's the OH stretching frequency for the species on the right?
I don't know what those are.
Yeah. You should compare them.
But that's going to be what you're measuring is the bound state. I'm talking about in the transition state where I pull off a proton, there has to be an electron transfer. The electron transfer is coming in from the metal to stabilize that deprotonation, the same way we do it here. So you're looking at the reactant state. I'm talking about as I activate that bond, there has to be an electron transfer there.
You guys can continue that discussion. Other questions?
Can you go over again the origin of the isotope effect on hydrogen? The origin of the isotope effect. Can you show
Origin of the isotope. Oh, yeah. This one. For which case? In this case one here? So in this case, they're looking at basically deuterated methanol versus non-deuterated methanol to carry out this chemistry. And you see that basically there is a change, which means that it's easier to transfer hydrogen than to transfer deuterium. And this is likely or can be involved in the rate determining step or pre-equilibrium step. So it says that the OH bond is playing some sort of role in the rate determining or pre-equilibrium step in activating the O2.
So my question specifically is the origin of that effect from vibrational changes to entropy or from tunneling or recrossing mass of the hydrogen?
It's the usual mass of the hydrogen, and basically it's going to be slower in terms of carrying out basically that chemistry if it's a hydrogen than if it's the heavier deuterium.
Any other questions?
Thank you for the good talk. In the case of like a 4-electron OR process, would you also propose that the rest of the electron-proton transfer events also occur through this kind of co-absorbed co-catalyst species, or is there something special about the first barrier of hydrogen to absorb O2 species that specifically for that step you would propose this kind of co-catalyst mechanism?
Can you repeat the first part?
Yeah, so basically for the 4-electron process, but you also propose this kind of co-absorbed mechanism as well for the rest of the electron transfer.
Yeah, it's similar because again it's the activations transferring of the proton. We did look at direct activation. We did look at direct hydrogen addition to it to activate the O2. Neither of them, both of them showed much higher barriers than this process of proton and electron transfer.
Other questions? All right, if not, let's thank the speaker. Hold on a second.